Everyone, this is audio recording for visually impaired students. Fats, oil and detergents. Introduction. Oil and fats are widely distributed in nature both in animals and plant kingdoms. In animals they are present under the skin and in muscles, but in plants they are mainly found in the seeds. Some important examples of fats are butter, lard, tallow, beef, etc. While groundnut oil, cotton seed oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oil, etc. are important examples of vegetable oils. Fats and oils are one of the three major constituents of our food, the other two being carbohydrates and proteins. In fact, fats and oils serve as energy reservoirs for the animals. In human beings, only a few hundred of grams of glycogen can be stored, which can barely supply the body's energy need for about 12 to 18 hours. In contrast, large amount of fats can be stored, which can supply the body's energy need for about 8 weeks. Besides this, oil and fats serve as raw material for a number of industries such as soap, paints, varnishes, and vanaspati ghee, etc. Natural fats. The fats obtained from animal source such as butter, lard from hogs, and tallow from sheep, goats, etc. are called natural fats. This name is simply given to differentiate these fats from those fats which are obtained by hydrogenation of oils. Edible and non-edible oils. Oils such as groundnut oil, sunflower oil, soybean oil, rapeseed or mustard oil, olive oil, sesame oil, which are used for cooking purposes, are called edible oils, while oils such as cotton seed oil, linseed oil, castor seed oil, moha oil, which are used in soap, paints, varnishes, the lacquer industries, are called non-edible oils or industrial oils. On the basis of iodine values, oils have been classified as drying, semi-drying and non-drying oils. Industrial oils may also include essential oil or mineral oils. Essential oils such as rose oil, jasmine oil, lavender oil, eucalyptus oil, peppermint oil, and are volatile oils isolated from plants. Essential oils may be hydrocarbons, alcohols, aldehydes, ketone, ester, etc. For example, peppermint oil contains methanol as its chief constituent. Essential oils are mainly used in perfumes, cosmetics, and in pharmaceutical products. On the other hand, mineral oils is a mixture of saturated and unsaturated hydrocarbons and not esters or triglycerides. They cannot be saponified. They are called oils simply because of their physical appearance. They are non-edible and are mainly used as fuels. Triglycerides, composition of oil and fats. As stated above, fats and oils are triacetyl and with aliphatic monocarboxylic acids. In other words, they are triglycerols and are commonly known as glycerides. Fats and oils may be represented by the general formula triacylglycerol or triglyceride. Fatty acid, with only a few exceptions, all the monocarboxylic acid isolated from fats and oils are straight chain compound containing 3 to 18 carbon atoms. Further, with the exception of only C3 and C5 acid, all the other acids found in fats and oils contain even number of carbon atoms. The chief saturated fatty acids present in oil and fats are lauric acid, myristic acid, palmitic acid. Besides saturated fatty acid, unsaturated fatty acids containing one or more double bonds in cis orientation may also be present in oil and fats. The chief unsaturated fatty acid present in oil and fats are oleic acid, linoleic acid. Classification of glycerides. The three fatty acid and glyceride may be same or different. Therefore, glycerides are classified as simple or mixed glycerides according as they have the same or different acid residue. For example, tripalmitin or glyceryl tripalmitate. Glycerides are further classified into saturated and unsaturated glyceride according as they contain saturated fatty acid residue or unsaturated fatty acid residue. Both simple and mixed glycerides are found in nature, oils and fats. In fact, oil and fats are complex mixture of mixed glycerides along with small amounts of simple glycerides. Chemical difference between oils and fats. The main difference between oils and fats is the proportion of saturated and unsaturated glycerides. Triglycerides with higher proportion of saturated acid residues such as palmitic acid, stearic acid are solid at ordinary temperature and are called fats, while those with higher proportion of unsaturated acid residues such as oleic acid, linoleic acid are liquid at ordinary temperature and are called oils. Melting point of glycerides. As stated above, Fatty acids have one or more double bonds having less stable cis stereochemistry. For example, oleic acid has one cis double bond at C9. Linoleic acid has two double bonds at C9 and C12, while linoleic acid has three cis double bonds at C9, C12, and C15 position. These cis double bonds have vital biological importance in the solid state. The molecules of saturated fatty acid fit closely in the crystal lattice due to their zigzag tetrahedral structure. On the other hand, cis unsaturated fatty acids have a band at the double bond and hence do not fit closely, thereby lowering their melting points. Chemical properties. Fats and oils being triester of glycerol show all the reactions of simple esters. In case the glycerides contain unsaturated fatty acid residues, they also show the usual addition oxidation reaction of alkenes. Some important reaction of fats and oils are given below. Hydrolysis. Fats and oils are readily hydrolyzed by treatment with superheated steam, mineral acid, or alkalis. Hydrolysis by superheated steam or mineral acids gives a mixture of fatty acids and glycerol. However, when the hydrolysis is carried out by alkalis, glycerol salts of fatty acids are formed. Since the salts of higher fatty acids thus formed are used as sorbed, the alkaline hydrolysis is commonly called saponification. In the digestive system of human beings and animals, fats and oils are hydrolyzed glycerol and fatty acids by a number of enzymes called liplases. 2. Hydrogenation. Oils which contains a large proportion of unsaturated glyceride add on hydrogen in the presence of finely divided nickel as catalyst to form solid fat. This process is called hydrogenation or hardening of oils. It is similar to catalytic hydrogenation of alkenes and involves the reduction of double bonds present in unsaturated glyceride to form saturated glycerides. This process is extensively used for the manufacture of vanaspati ghee from groundnut, peanut, and sunflower and other edible oils. Hydrogenation is never carried out to completion but is stopped as soon as the fat of consistency comparable to ghee is obtained. The completely hydrogenated fats are too hard to be useful as kitchen shortenings. The main advantage of hydrogenation is that of compared to oils, fats have better storage qualities and do not become rancid easily. 3. Hydrogenolysis. Conversion to alcohols, fats and oils on treatment with hydrogen at high temperature and pressure and in presence of copper chromite as catalyst undergo reductive cleavage to form glycerol and long chain aliphatic alcohols. The splitting of a fat or an oil to glycerol and a higher long chain alcohol by hydrogen is called hydrogenolysis. The long chain alcohols as produced are used for the manufacture of synthetic detergents. 4. Transesterification. Fats and oils can be converted into simple esters of carboxylic acid such as methyl, methyl esters, etc. by transesterification. It involves the treatment of a fat or an oil with a large excess of a suitable alcohol in presence of acidic or basic catalyst. The process of transesterification is quite useful for the large-scale preparation of long-chain fatty acids and long-chain primary alcohols of high purity. For this purpose, the mixture of methyl ester obtained by transesterification is subjected to fractional distillation to separate the individual esters. These, upon hydrolysis, yield fatty acids of high purity. Alternatively, the individual methyl esters are reduced to get long-chain primary alcohols. Addition of halogen. Like alkanes, unsaturated glycerides add halogen across the double bond to form addition products. The addition of iodine is usually carried out by treating the fat or the oil with iodine in presence of mercury chloride as catalyst. Since the amount of iodine used is proportional to the number of double bonds present, therefore this reaction is used for the determination of extent of unsaturation in a given fat or the oil. Rancidity. When fats and oils are exposed to warm air and moisture for a long time, they develop a disagreeable smell and taste. The process is called rancidity and involves the hydrolysis of ester to produce fatty acids and oxidation at double bonds to form short chain acids and aldehydes. These short chain acids and aldehydes are volatile and have offensive smell. Therefore, they impart unpleasant odors to oils and fat. Rancidity is of the following two types. Hydrolytic rancidity. This type of rancidity is caused by the liberation of lower fatty acids by hydrolysis of triglycerides. For example, when butter is exposed to warm air and moisture, the hydrolysis of the glycerides in butter yields butyric acid and other volatile acids with unpleasant odors. The process of hydrolysis is catalyzed by enzymes which are provided by the microorganism present in air. This type of hydrolytic rancidity can, however, be checked by keeping the butter covered in a refrigerator. Oxidative rancidity. This type of rancidity is caused by oxidation of the unsaturated triglycerides by air to form short-chain acids and aldehydes having unpleasant smell. It is believed that first the ester linkages are hydrolyzed to unsaturated acids which undergo oxidation at the site of double bonds to produce short-chain acids and aldehydes. Oxidative rancidity can be prevented by the addition of certain chemicals called antioxidants. Two antioxidants which occur in the natural fats are called vitamin C and vitamin E. Analysis of fats and oils. Fats and oils are extensively used in a number of industries. Therefore, it is essential to check the quality of a given fat or an oil. This involves the determination of physical constants such as melting point, specific gravity, refractive index, etc., and chemical constants such as acid value, iodine value, saponification value, Rm value, etc. Some important chemical constants are described below. Acid value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the free fatty acid present in 1 gram of fat or an oil. The acid value is determined dissolving a known weight of the given fat or the oil in pure neutral alcohol and titrating against standard QH solution using phenolphthalein as indicator. The acid value is a measure of free acid present in a given fat or oil. A high acid value indicates that the given sample of the fat or oil is quite old and has become rancid. Saponification value. It is defined as the number of milligrams of potassium hydroxide required to completely saponify 1 gram of the fat or oil. In other words, it represents the amount of potassium hydroxide in milligrams required to neutralize the fatty acids formed as a result of complete hydrolysis of 1 gram of the fat or oil. Saponification value is determined by refluxing a weight quantity of the fat or oil with the known excess of standard alcoholic potassium hydroxide solution and then titrating the unreacted alkali against a standard acid. For example, saponification values of triurate and tripalmitin can be described as follows. Thus, the saponification value gives an idea about the molecular weight of the fat or the oil. Obviously, smaller the saponification value, higher is the molecular weight. For example, tripalmitin molecular weight is equals to 806, has a saponification value of 208, whereas trilorate with molecular weight 638 has a saponification value of 263. The saponification value also indicates the length of carbon chain of the acid moiety present in the oil and fat. The higher the saponification value, greater the percentage of short chain fatty acid in the glycerides of the fat or oil. Butter with short chain fatty acid has saponification values between 210 to 230, whereas soybean oil has saponification values between 189 to 195. Saponification value is used to determine the adulteration of a fat or an oil with some other oil or fat with lower or higher saponification value or even by some unsaponifiable matter. 3. Iodine value. It is defined as the number of grams of iodine that will combine with 100 gram of the fat or oil. Iodine value may be determined by any one of the following two methods. 1. Hubble's method. In this method, a solution of a known weight of the fat or oil in CCl4 is allowed to react with a known excess of standard solution of iodine in ethanol in presence of mercury chloride as catalyst. The unreacted iodine is then determined by titrating it against standard sodium thiosulfate solution using starch as indicator. For example, the iodine value of triolene may be calculated as follows. Witt's method. In this method, a solution of the more reactive iodine monochloride, in English acetic acid, is used in the place of iodine and mercury chloride. A known weight of the oil and fat dissolved in CHCl3, which solution is then added. ICl adds across the double bond, then ICl left unused and then treated with KI solution to liberate an equivalent amount of iodine. The liberated iodine is then titrated against standard hypo solution using starch as indicator. The amount of ICl that has added across the double bond is therefore determined using the following relation. Iodine value is equals to V1 minus V2 into N into 12.7 upon W, where V1 volume of hypo used for blank titrations, V2 have volume of hypo used for unreacted ICl, and is normality of the hypo solution, W is the weight of the oil or fat taken. Iodine value is a measure of the extent of unsaturation present in an oil or fat. Higher the iodine value, more unsaturated is the oil or the fat. For example, iodine value of linseed oil is 170 to 185, tung oil 163 to 171, soybean oil 127 to 138, sunflower oil 140 to 156, olive oil 18 to 100. RM value. It is defined as the number of milliliters of 0.1 normal KH required to neutralize the steam volatile fatty acids obtained by complete hydrolysis of 5 gram of the fat or oil. To determine the RM value, a known weight of the fat or oil is completely saponified with alkali. The resulting solution is acidified with dilute H2SO4 and then subjected to steam distillation. Distillated, which contains the volatile acid, is then titrated against 0.1 normal QH solution. The RM value is then calculated as follows. RM value is equals to volume of 0.1 normal QH used for neutralization into 5 upon weight of the fat or oil taken. RM value is a measure of the volatile fatty acid residues present in a given fat or oil. It is highly useful for testing the purity of butter and desi ghee, which contain a relatively high proportion of glycerides, butyric acids, and other steam volatile acid residue. The RM value of adulterated butter is always lower than of pure butter. Industrial oil or vegetable origin drying oils. Certain oils such as linseed oil, tung oil, perilla oil, etc., when exposed to air in thin layers, form hard and tough water-insoluble solids. This process is known as drying, and such oils are called drying oils. Oils like olive oil and groundnut oil, etc., which do not dry on exposure to air, are called non-drying oils, and those which dry slowly, such as cottonseed oil, are called semi-drying oils. Chemically, drying oils contain a high percentage of unsaturated glyceride as shown by their high iodine values. On the other hand, non-drying oils have low iodine values, while semi-drying oils have intermediate iodine values. For example, drying oils have iodine values above 150, non-drying oils have iodine values less than 100, while semi-drying oils have intermediate iodine values. Unsaturated glycerides contain linoleic acid, and linoleic acid has a saturated fatty acid residues. This contains 2 and 3 isolated double bonds respectively. In general, drying oils containing unsaturated glycerides with conjugated double bonds dry more rapidly than those containing isolated double bonds. Drying oils are used as medium for paints, varnishes, and lacquers. In fact, paints are suspensions of some pigments or the organic coloring matter is linseed oil, to which some turpentine oil has been added. It is thinner. When these paints are applied on any wooden or iron surface in thin layers and quickly dry up to form a tough organic film which protects the surface being painted. Mechanism. The actual process of drying does not simply involve removal of moisture or evaporation of solvent, but involves organic complex changes. It is believed that the reactive allylic hydrogen present in unsaturated glycerides are first attacked by oxygen to form hydroperoxy compounds, which then combine with the allylic hydrogen of the other glyceride molecules, forming peroxide bridges. The monomer molecules thus obtained subsequently undergo polymerization to form a tough network solid. The whole process is sketched below. Soaps. Substances like soaps and synthetic detergents, which concentrate at the surface of the solution or interface from surface films, reduce surface tension of the solution, help the removing dirt and dust by emulsifying grease, are called surface active agents or surfactants. The molecule of a surfactant contains two characteristics, one of which is water soluble and the other is oil soluble. Soaps are sodium or potassium salzophyre fatty acids such as palmitic acid and oleic acid. These soaps are generally obtained by the hydrolysis of oils and fats with aqueous alkalis. The process is called saponification of oils. Fats, for example, the fats and oils commonly used for soap manufacture are tallow, lard, olive oil, linseed oil, mahuva oil, rapeseed oil, coconut oil, and palm oil. Soaps containing 12 to 18 chain atoms have good cleansing action. Soaps with 12 carbon atoms are comparatively soluble in water, whereas soap containing 18 to 22 carbon atoms are not useful as soap because of their insolubility in water. Sodium soaps are generally hard and called hard soaps. These are used for washing of clothes. Potassium soaps, on the other hand, are more expensive and produce a softer lather and hence are called soft soaps. They are used for making shaving cream, shampoos, and liquid soaps. Transparent soaps are prepared by dissolving ordinary soaps in alcohols and removing the insoluble part by filtration. Evaporation of alcohol leaves behind transparent mass. Soaps are 100% biodegradable, that is, microorganisms present in sewage water can completely oxidize soap into CO2. As a result, it does not create any pollution problems. However, soaps have two disadvantages. Soaps cannot be used in hard water since calcium and magnesium ion present in hard water produce curdy white precipitates of calcium magnesium soaps. Insoluble free fatty acid which adhere to the fabrics and thus block the ability of soaps to remove oil and grease from fabrics. Synthetic detergents. These days, in place of soaps, the substances which are being largely used as cleansing agents are synthetic detergents. As the name suggests, they are obtained from purely synthetic chemicals as compared to soaps which are derived from chemicals which are obtained from natural sources like oils and fats. In fact, synthetic detergents are sodium and potassium salts of long chain alkyl hydrogen sulfates or aryl sulfonic acid. Unlike soaps, magnesium salts or detergents like their sodium or potassium salts are also soluble in water. Hence, synthetic detergents do not form curdy white pipette with hard water. Further, they can also be used in acidic solution. However, synthetic detergents have only one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution. Synthetic detergents are of following three types. Anionic detergents, these are called because a large part of their molecules are anions. These are of two types. Alkyl sulfates, they are obtained from long chain alcohols by treatment with concentrated estrus of 4 followed by neutralization with NaOH. Some important examples of this type of detergents are sodium lauryl sulfate, C11H23CH2OSO3 negative Na positive, and sodium stearyl sulfate, C17H35CH2OSO3 negative Na positive. Sodium lauryl sulfate is also called sodium rhodecyl sulfate and is used in shampoos and cosmetics. These sodium alkyl sulfates are 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfate which is a soluble material, whereas soaps reacts with acidic solution to form insoluble fatty acids. B. Alkyl benzene sulfonates. These are obtained by conversion of benzene into long chain alkyl benzene followed by sulfonation neutralization with NaOH. The most widely used domestic detergent is the sodium para and diodecyl benzene sulfonate. Alkyl benzene sulfonates, in which the phenyl group is either attached to the end of the long alkyl chain or any other secondary position, have high biodegradability and hence are called soft detergents, while alkyl benzene sulfonates having branched chain alkyl groups have poor biodegradability and hence are called hard detergents. To differentiate these detergents on the basis of biodegradability, alkyl benzene sulfonates having long straight chains such as sodium para and dodecyl benzene sulfonate and sodium 2-dodecyl benzene sulfonate are called LAS detergents, while those having branched chains are called ABS detergents. An important example of ABS detergent is hard or non-biodegradable ABS detergent. It is prepared by FC reactions of tetramer of propylene with benzene followed by sulfonation neutralization with alkali. Cationic detergents. These are quaternary ammonium salts containing one or more long chain alkyl groups. These are also called invert salts because their surface activity is due to the positive ion or not to a negative ion, as in alkyl hydrogen sulfate detergents. Being more expensive than the anionic detergents, they find limited use. Besides being good cleansing agents, they possess germicidal properties and therefore they are widely used as germicidal in hospitals. 3. Non-ionic detergents. These are esters of high molecular mass alcohols obtained by reaction between polyethylene glycol or stearic acid. These may also be obtained from long chain alcohols by treatment with excess of ethylene oxide in presence of a base. Like alkyl sulfates, ethoxylates, and also biodegradable, hydrogen bonding to the numerous oxygen atoms makes the polyether end of the molecular water soluble. Alternatively, the ethoxylates can be converted into sulfates and used in form of their sodium salt. Some liquid dishwashing detergents are of non-ionic type. Composition of a detergent cake. A cake of detergent contains about 20% of addictive detergents and an equal amount of sodium sulfate to make up the bulk of the powder. A further 30 to 50% of the sodium tripolyphosphate or STPP is added as an additive. It coordinates with Ca2 positive and Mg2 positive ions present in hard water and thus enhance the cleansing efficiency of the detergent. Other ingredients include sodium perborate, which act as the bleaching agent, and some optical brighteners or fluorescers, that is organic compounds which make yellow clothes appear white, or some foaming agents. Detergent pollution. Detergents having branched chain hydrocarbon chains cause pollution in rivers and other waterways. The reason being that side chains stop bacteria from attacking and breaking chains. This results in slow degradation of detergents molecule leading to their accumulation, since unbranched chains are more prone to attack by bacteria. Therefore, in most of the detergent used these days, the branching is kept to a minimum so that the detergent become easily biodegradable and pollution is prevented. The second serious environmental problem is caused by phosphate additives, that is STPP, which are discharged into rivers and lakes from sewage system. As such, phosphate is not a pollutant but is actually a fertilizer. This excess of phosphate promotes the growth of water plants, which in turn deplete the water of available oxygen for fish and other aquatic animals. As a result of want of oxygen, water animals die and rot. In other words, lake become full of dead animals. Vegetation hence ceases to act as a source of potable water. In view of these environmental hazards, government of many countries have passed a law to reduce the use of phosphate additives in detergents to mitigate this source of pollution. Cleansing action of soaps and detergents. All the soaps and detergents contain two characteristics groups, that is water soluble group and an oil soluble. As a result, one end of the molecule of a soap or detergent tends to go into oil phase and other tends to go into the water phase, with the net result that the material soap or detergent concentrates at the surface of the solution interface. The dirt is generally held to a dirty surface by a thin film of oil or grease. When the dirty surface is treated with soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolved in oil or grease and the carboxylate group of the soap or the sulfonate group of the synthetic detergent is held by surrounding water. This lowers the surface tension between water and grease. As a result, a stable immersion of oil in water is found when the surface or the cloth is mechanically scrubbed. The loosened dirt particles are adsorbed by colloidal soap or detergent particles and ultimately washed away. Thanks for watching.